Accretion of Suricta with DPDK for traffic. Monitoring using optimized detection system. IDS/IPS. Abstract. In the era of Internet with rapid growth of advancing technologies, the network security concerns are increasing prominently as the number of network attacks has attracted more professionals' attention. To ensure computer system protection, the Intrusion Detection System, IDS, and Intrusion Prevention System, IPS, engine is been introduced as high-performance network for Suricata and a network monitoring tool with open source which is owned by Open Information Security Foundation, OISF. DPDK, Data Plane Development Kit, adopts polling method for data packet processing, which saves CPU interruption time, memory copy time, and provides the application layer with a quick and effective data packet processing system, making network applications more convenient to create. DPDK Suricata is introduced in this paper for multiple packet ACL rules support with the use of DPDK poll mode driver for traffic analysis to get better performance. RxTX threads with DPDK ports for packets interface, pre-parsing filter, and rule filters to allow the relevant packets. So, it helps to build ACL key for IPv4 and IPv6, as DPDK Suricata is also added with worker mode like IPS, IDS, bypass modes to configure and run the rules accordingly. Keywords: DPDK, Suricata, Intrusion Detection System, Intrusion Prevention System, ACL, Poll Mode Driver, Rules. Introduction. In today's business, networks are emerging to a large extent. Managing high traffic is so tough and transmit 10 GB per second on a backbone. So Suricata's multi-threaded architecture allows its users to scale horizontally over a single appliance by adding threads for packet processing as the amount of traffic makes it obligatory. Suricata is an IDS/IPS engine based on rules that uses externally built rule sets to track network traffic and send system administrator warnings when unusual events occur. Designed to be companionable with existing components of network protection, Suricata provides simplified functionality of output and pluggable library options to accept calls from other applications. Any suspicious activity or intrusion is usually recorded or centrally collected using a network for security information and event management. DPDK packet processing is using polling to achieve packet processing, thereby saving time for CPU interruption and time for memory retrieval. DPDK provides a simple and efficient application layer packet processing method which makes network application more feasible. DPDK Packet Capture Library calls PMD's network card feature to verify if the packet has been captured to analyze the data packet which is stored in cache. In our paper we discuss about DPDK and Suricata performance by integrating Suricata into DPDK platform for more secure to monitor the networking traffic with 3-tuple ACL rules can overcome the network security issues in a large business network to detect and prevent them by introducing Suricata pipeline for better performance. So, the ACL rule we follow are alert, drop, and forward. As access control list helps to manage and mitigate traffic accordingly by avoiding cyber attacks if any encountered. By selecting the IP mode to be IDS or IPS does the job accordingly. Configure the DPDK interface on a Suricata work pipeline as this helps in knowing how many interfaces are bound to our user application. DPDK ACL in which shows the packet processing analysis by using DPDK poll mode drivers which helps to send the relevant IPv4 and IPv6 on Suricata worker pipeline. To ease of use, Suricata is one of the free software intrusion detection systems, which utilizes remotely developed run sets to screen sniffed activity and alarm when suspicious occasions arise. One of Suricata's distinctive features, particularly as opposed to Snort, is that it has a dynamic port-agnostic protocol security capability. This means that when these interact over non-standard ports, it can recognize some of the more popular application layer protocols, such as HTTP, DNS, and TLS. Network for malicious activity or policy violations and network monitoring tool for securely transmitting packet into an end host. If positioned at a strategic point or points within a network to track traffic to and from all devices on the network, An IDS can conduct a passing traffic analysis and compare the traffic transmitted to the database of known attacks on the subnets. The warning can be sent to the administrator until an attack is detected or an irregular activity is sensed. An intrusion prevention device operates by actively monitoring transmitted network traffic for malicious activities and established patterns of attack. The IPS engine analyzes network traffic and continuously compares the bit stream for identified attack patterns to its internal signature database. Intrusion detection mechanisms may also make monitoring and analysis more difficult, such as observing and responding to unusual traffic patterns or packets. Can include detection mechanisms. Data Plane Development Kit, DPDK, is a set of data plane libraries which is managed by Linux Foundation as it is open source software project. The network interface controller with poll mode drivers to offload TCP packet processing from the operating system kernel to user space. Using the interrupt-driven processing provided in the kernel, this offloading achieves higher efficiency and packet throughput than is possible. In this figure 2 describes a core component of DPDK as it consists of environment abstraction layer, ring buffer management, memory pool management, network message buffer management, timer management, and specifying detailed structure. It picks up and sets a single P thread on each core, and then becomes a thread run to completion. DPDK uses SRIOV to bypass the Linux kernel for direct ports control. The PMD uses SRIOV virtual feature interfaces 1 per PMD to manage the connection to port hardware. The applications, along with many utilities, use DPDK generic APIs to access and manage the ports. As each application runs on a single core for better performance, applications need to share data, then the application needs to provide the means to communicate, and DPDK contains several types of ways to communicate between lockless rings, semaphore. The application needs to survey the ports that it wants to accept data packets called MBUFs, root_MBUF. 3 Literature survey. In this section the research scholars' work has been discussed with various way of bestowing knowledge out by interested key domain to highlight network-related issues. With the internet usage exceeds to peaks in day-to-day life by accessing various applications in a huge traffic, the flow of packet processing is analyzed in their setup to get better performance. DPDK and Suricata has been a main work carried out by the authors for their research as security concern and performance of an application using various environments. So, they are detailed below with the work carried by the researchers. 1. Nagasuriya Lakshmi ETAL use open source IDS tools for performance analysis of Suricata and Snort with respect to speed and size of a packet. The packet size ranging from 512, 1000, and 24, 2048 with speed of internet from 200 Mbps, 400 Mbps, 600 Mbps, 800 Mbps, 1 Gbps. With 2 protocols IETCP and UDP are compared with Snort and Suricata, so the packet loss is noticed at both the end. The increase in packet size with decrease in packet loss thus follows reciprocal relationship between them. The rate of packet size increases with internet speed simultaneously. 2. Donjian ETAL comparison of Snort and DPDK to enhance performance using 100 Mbps to 1000 Mbps using DPDK-based intrusion detection system solves the problem of traditional Snortids, which detects all the packets sent. Whereas Snortids detect less compared to DPDK-ids, so it optimizes to better performance of an various packet size and higher speed for network flow. More than 1000 Mbps gives better result. 3. Jong ETAL Flowitcher DPDK, a lightweight high-speed software traffic controller capable of generating fine-grained per packet and per flow statistics with 6 4B packets at a line rate of 10 Gbps, using only 2 CPU cores. The method leverages the RSS hash, previously determined by the NIC and available as packet metadata, as a flow identifier to prevent unnecessary computation and memory access, and employs a cautious design where flow tables are matched with line boundaries of caches. Flowitcher DPDK outperforms state-of-the-art alternative solution to its environment, and comprehensive parameter tuning was conducted. 4. Martino ETAL proposed DPDK stat, a high-speed statistical traffic analysis, STA, that combines the Intel DPDK system with the passive traffic analyzer IJERT to achieve a line rate processing of 40 Gbps. In addition to publishing a concise assessment using real-time traffic traces, the architecture challenges to achieve scalability. A periodic package acquisition strategy, leveraging the latest SCHED deadline Linux scheduling discipline, never considered in previous works, conduct an in-depth analysis to reduce timestamp errors and prevent packet reconfiguration and losses. 5. Kevin ETAL supported level for supervisory control and data acquisition, SCADA, protocols in well-known open-source intrusion detection, IDS, systems. Identify and improve a different IDS, Suricata, to provide support for the monitoring threats against SCADA devices that run the Industrial Control Protocol Ethernet/IP, ENIP. At an 18 Mbps throughput reflecting several SCADA networks, Suricata can run viably on hardware platforms with smaller memory and a less powerful CPU. Adding a module to process the Suricata ENIP rules did not affect output in terms of CPU utilization or packet drops. Observed that there are varying levels of the three most popular open-source IDS systems. Support to 3 SCADA protocols. Description of the new protocol by rule. Analyze the rule and store it in the data structure that fits the rule. Add an ENIP packet parser. ENIP Module 1 focused on the analysis of individual packets and of packet streams. In the end, the other was adopted and accepted for integration as part of Suricata's main distribution. 4. Methodology. With rapid growth of high-speed networks and increasing complexity in cyber attacks, high-performance IDS tools are needed to process packets quickly, reconstruct streams and apply pattern matching for signature-based threat detection. The efficiency of these systems depends on many factors, including the efficiency of its pattern matching engine in which incoming packets are tested. In the Figure 3, as Suricata plays very important role in various aspects, especially with security concerns in the network. By processing a data packet has a capability to detect and analyze the traffic pattern. It is compatible with other environments for more efficient and higher performance with their respective environment, like DPDK Suricata is been introduced. Suricata has been developed as a next phase IDS platform with IPS, Intrusion Prevention System, capabilities configured to be backwards compatible with SNORT rule sets. Suricata has been designed as a multi-threaded system, allowing multiple cores to be exploited. In above architecture there are n number of threads which performs different actions, as packet acquisition, which collect huge amount of data which is received from the network is been sent from thread 1 to packet queue to forward the packets in thread 2. Thread 2 receives packet and start decoding and analyzing the network traffic, and with the help of packet queue is been forwarded next thread I.E. Thread 3, as packet stream are further portioned into substreams and distributed across the processing task for parallelism with load balancing. In order to allow maximum use of the computing power available in a multi-core system and to avoid processor race conditions, there is a need to ensure even load balancing, LB, between cores. The aim of Suricata's LB is to evenly dispatch the workload across all cores and minimize idle time. Suricata therefore shows superior performance on multi-core machines with rule sets designed for Suricata. As a result, it can easily analyze huge traffic volumes without having to cut down on the number of laws. Suricata also stands out for its ability to provide visibility into the application layer and faster HTTP stream parsing. It may analyze HTTP traffic regardless of the port number used and does not rely on port numbers for traffic identification. Suricata also enables inspection of streams within the protocol and can therefore extract files for further analysis from HTTP sessions. V. Implementation. A proposed workflow. As discussed in introduction, Suricata is an open-source software project which gives better performance when run on a DPDK platform for better efficiency and packet processing. The DPDK environment for packet processing applications allows for 2 configurations, run-to-completion and pipeline. In the run-to-completion model, the RX descriptor ring for packets is pulled through an API in a specific port. Packets are then processed at the same core and put through an API for transmission on a port's TX descriptor ring. One core pull in the pipeline model is rings one or more RX descriptors of a port via an API. Packets are obtained and passed through a ring to another hub. The other core continues processing the packet, which can then be positioned on a port's TX descriptor ring for transmission through an API. A pole mode driver, PMD, comprises of APIs which are provided to configure the devices and their respective queues through the BSD driver running in user space. In addition, a PMD accesses the RX and TX descriptors directly without interruptions, except for interrupts with connection status change, to instantly receive, process and transmit packets in the user's application. The overall software optimization strategies must be considered and balanced against available low-level hardware-based optimization features, CPU cache properties, bus speed, NIC PCI bandwidth, and so on, to achieve optimum performance. The expense of invoking the root_eth_tx1 function between multiple packets. Enable root_eth_tx burst to take advantage of burst-oriented hardware features, prefetch data in cache, use of NIC head/tail registers, to reduce the number of processor cycles per packet. For example, avoiding excessive read memory accesses to ring transmitter descriptors, or consistently using pointer arrays that match cache line boundaries and sizes exactly. To suppress operations that would otherwise be inevitable, such as ring index wrap back control, apply burst-oriented device optimization techniques. B. Experimental setup. The test analysis is performed based on the rule set on Suricata. DPDK in turn uses two protocols, they are TCP and UDP. In the process of setup we mainly need DPDK PTN, DPDK 19.11 Suricta _3.0 and rules. Our test is mainly focusing on two protocols with the scenario of 64,128,512,1024 byte line rate and assigning one DPDK thread for 10G interface for IPS/IDS. In rule set our analysis is focused only on alert and allow to stress single worker thread. Mainly focusing on DPDK RX_burst and TX_burst to capture the line rate of packets, and the threshold limit is measured only for single worker thread with minimal 0_copy. As per Figure 4. 6 results. Figure 4 shows the traffic received from the interface is run on packet acquire loop function of Suricta, as there is no dedicated worker thread to handle the traffic in the interface provided, so the packets scheduled for worker thread fetches from PMD interfaces which is in user space. Figure 5, 6, 7, 8, 9 and 10 depicts the traffic is received in the forwarded to packet acquire loop function with the help of ring buffer. It is receiving thread accepts in pipeline model, which will not allow on same core with YAML config, so the worker thread scheduled fetches packets by dequeuing ring buffer which is connected to it in the user space. The CPU affinity is checked for getting enough core available to receive traffic on interface which are present in DPDK and run on dedicated DPDK. As we add rule or signature, we must extend the filtering to rule the matched packet by allowing packets forwarded to copy_interface and further the worker thread process for matched rules. Figure 6, the number of packets sent and received on port 1. The graph above in Fig 5 and Fig 6 is tested for port 0 and 1 with no rule hit in 64,128,256,512,1024 byte line rate as in the graph. Blue, red, green, and purple indicates packet size per rate. Figure 7, the number of packets sent and received on port 0 with rule match. Interface run on specified DPDK, then this packets are. The graph shown above in Figure 7 and Figure 8 is validated for alert rule in port 0 using YAML config and the rule set as alert UDP any, alert TCP any. This are tested in 64,128,256,512,1024 byte line rate with 0,25,50,100 packet size per rate by RX and TX. As the tests are done using two ports dedicated to Suricata DPDK, the graph shown above for allow rule in port 1. So this are done for one DPDK thread and one worker thread for 2*10G. 7. Conclusion and future scope. Suricata is a high-performance monitoring tool for IPS and IDS with the utilization of single DPDK worker thread with the network traffic received on the interface by allocating dedicated library using CPU affinity, YAML config, which accelerates the IDS and IPS processing of Suricata worker thread to perform better. The future scope of work is to add multi-worker thread to core, to allocate and deallocate struct peaked using them buff sector, pre-parsing the frame to accelerate the decode logic. Acknowledgement. I would like to acknowledge the Ramaiah Institute of Technology College Management, staff, and my mentor for their very indeed and extreme support and encouragement to do this research.